The Great Pyramid is a mountain of stone built without any machines. How did they move those blocks? This video will show you the simple physics that made it possible. You will learn how ancient engineers used levers, ramps, and rollers to solve problems we still face today. How did they make a stone statue walk across an island or float a granite needle down a river? By the end, you will see these ancient wonders not as magic, but as masterful logic. What does it truly mean to move a mountain? That first shove is always the hardest. Picture a single worker, muscles straining, leaning all their weight into a stone slab taller than they are. The stone groans, perhaps shifts a tiny fraction, but refuses to slide. This is the invisible wall every ancient builder faced first, the formidable grip of static friction. It is the force that locks an object in place, demanding a tremendous initial push just to get it started. Once moving, the resistance drops, becoming kinetic friction, a much more manageable force to maintain. The genius of early engineering was not in overpowering this friction with brute strength, but in outsmarting it. They learned to cheat. By placing a layer of wet clay or slick mud beneath the stone, they created a lubricated plane. Suddenly, the rough, grinding contact between stone and earth was replaced by a slippery, watery interface. The coefficient of friction, that measure of grip between two surfaces, plummeted. What required the combined force of 50 men might now need only 10. This was their first and most vital principle, to make the earth itself an ally in motion. They turned the ground from a holding cell into a highway. With this fundamental understanding, that initial, impossible shove became a calculated, achievable slide. The stone was now in play, ready for the next ingenious trick. But sliding a stone is one thing, lifting it is another. To raise a massive block onto a foundation or pivot it into a precise corner, ancient engineers turned to one of humanity's oldest and most elegant tools, the lever. Centuries before Archimedes would famously muse about moving the world with a lever and a place to stand, builders were already applying that very insight on their construction sites. The principle is beautifully simple. A lever is just a rigid beam, but when it pivots on a point called the fulcrum, it transforms force, pushed down with a modest effort over a long distance on one side, and the other, shorter side transmits a much greater force upward over a tiny distance. This is mechanical advantage in its purest form. Picture a team on a pyramid ledge. They've slid a multi-ton limestone block to the very spot it needs to rest. Now for the final inch, they wedge a stout timber beam under one edge of the stone, placing a smaller, rounded rock beneath the beam as the fulcrum. Then, in a coordinated rhythm, several workers throw their weight onto the long end of the timber. With a collective groan of wood, the impossible happens. That colossal block, defying its own immense weight, rises almost imperceptibly. A sliver of space opens beneath it. Immediately, another worker slides a thin stone chip into that gap, locking in that minuscule gain. They reset the lever, find a new purchase, and push again. Lift, shim, reset. Through this patient, rhythmic repetition, they walk the stone upward, degree by careful degree, until it settles perfectly level. This was not brute force, it was amplified intelligence. It was a hands-on mastery of torque and equilibrium, allowing a small team to command the obedience of a giant. The lever gave them control, the fine-tuning adjustment needed to make a mountain of individual stones fit together like a single, seamless puzzle. And once that stone was raised and set, a new challenge awaited: how to move it not just an inch upward, but hundreds of feet across the earth. Those levers provided the crucial final adjustments, but the monumental task of raising millions of stones to ever greater heights demanded a system, a permanent engineered solution. That solution snaked up the sides of the construction site in the form of vast earthen ramps. the inclined plane made colossal. This simple machine operates on a beautifully logical trade-off. To lift a heavy object straight up requires overcoming its entire weight at once, a Herculean effort, but tilt that effort onto a slope, and the required force is dramatically reduced. You are trading a short, brutal struggle for a long, manageable journey. The steeper the ramp, the harder the pull, but the shorter the distance. The gentler the slope, the easier the pull, but the longer the winding path to the top. Ancient engineers mastered this balance by constructing ramps of packed earth, brick, and rubble at a shallow angle. They transformed the impossible vertical lift into a horizontal drag. Teams of workers, perhaps chanting in rhythm, could now haul a sled bearing a multi-ton block up this artificial mountain highway. The force needed was still immense, but it was a sustained, shared effort spread over time and distance, something human muscle and coordination could achieve. Evidence points to different ramp designs for different phases. Early on, a single massive straight ramp might have risen from the quarry to the lower courses. As the pyramid grew taller, such a ramp would become impossibly long and unstable, so the design evolved. A zigzagging ramp, switching back and forth up one face, reduced the overall length while maintaining a gentle grade. Some researchers propose an even more elegant solution, a ramp spiraling up inside the growing structure itself, its builders dismantling it from the top down as they completed each level. Each ramp was a temporary mountain built to conquer a permanent one, a brilliant physical manifestation of a simple principle, trading distance for force to literally move mountains, one patient, sloping step at a time. Yet the ramp was only half of the equation, a static path for a dynamic problem. The real challenge was the sled itself, grinding its way inch by agonizing inch against the relentless pull of friction, even on that lubricated slope. The solution emerged not from a single brilliant mind, but from a simple, observable truth of the forest. A round log, when pushed, rolls. This observation sparked a revolution in transport, the invention of the roller. Picture a team halting a heavy sled. Instead of trying to drag it further, they kneel and place several freshly cut, sturdy logs perpendicular to its path, right up against the sled's runners. With the next heave, the stone lurches forward, but now it is not sliding, it is rolling. The sled's runners settle onto the logs, and as the team pulls, the cylindrical logs rotate beneath the load. In that instant, the builders transformed sliding friction into rolling friction, a force many times smaller and far easier to overcome. The stone now glides with a surprising smoothness. But a log only rolls so far before the sled passes over it, so a beautiful, rhythmic choreography begins. As the sled moves forward, workers at the back crouch down, retrieve the now uncovered logs, and rush them around to the front, placing them down once more in the advancing path. The stone, in effect, walks on a continuous, recycled track of its own making. This makeshift conveyor system allowed for the sustained movement of impossible weights across vast and varied terrain. Researchers believe a method like this was essential for moving the famous blue stones of Stonehenge, each weighing multiple tons, over a journey of more than 150 miles from their Welsh quarry. It was not magic, it was meticulous logistics, a perfect marriage of simple physics and human coordination. The rolling log turned geometry into motion, proving that the most profound engineering often lies not in creating new materials, but in reimagining the use of what is already there, a principle that would soon spin itself into humanity's next great invention. Yet even rollers have their limits, especially when the cargo becomes truly monumental. Imagine a single granite obelisk, a needle of stone weighing as much as 400 tons, destined to stand before a temple. Dragging such a colossus overland for miles would be a generational task of almost unimaginable difficulty. But if you could make the stone weigh less, the problem would transform entirely. And that is precisely what ancient engineers learned to do, not by changing the stone, but by changing the medium that surrounded it. They learned to make the stone float. In regions crisscrossed by rivers and canals like Egypt and Mesopotamia, the answer was not just on the land, but in the water. They understood intuitively a principle that would later be named for Archimedes, that an object submerged in a fluid is buoyed up by a force equal to the weight of the fluid it displaces. For a dense stone, this meant that in water, its effective weight could be reduced by nearly half. A 400-ton obelisk might only feel like 200 tons to the teams moving it. The implementation was a masterstroke of practical logistics. For an obelisk, they would likely construct a massive, reinforced barge, perhaps by lashing many boats together for stability. Using ramps and levers, they would carefully guide the stone onto this floating platform, a tense operation where precision prevented disaster. Once secured, the barge, now riding low in the water, could be towed by teams of rowers along the Nile. The river's current could even be harnessed to assist the journey. For other, less shapely megaliths, they might employ a different tactic, lashing sealed, empty pottery jars or inflated animal skins all around the stone. This added extra buoyancy, essentially turning the stone itself into a crude but effective vessel. The genius of flotation was its breathtaking efficiency. It turned a river from a barrier into the widest, smoothest, and most level road imaginable. It conserved immense amounts of human and animal energy, and it made possible the transport of stones so large that no land-based method could have managed them over such distances. This was the pinnacle of merging simple physics with environmental wisdom, using the water's own embrace to carry the weight of the mountain. But what happened when the stone reached its destination, dry and waiting on the bank? The final act of this ancient drama required one more ingenious application of force, a way to guide these floating giants back onto solid ground and raise them to their eternal stance. A river could carry the stone, but the final lift still defied gravity. For the delicate, precise work of raising a block onto a waiting wall or pivoting an obelisk upright, engineers needed more than levers and ramps, they needed control. The answer hung from a simple wooden wheel with a groove carved around its edge. This was the birth of the pulley, a device that performed a subtle but profound magic. It redirected force. Picture a team inside a temple courtyard. A massive lintel stone needs to be lifted 10 feet to cap a doorway. A single wooden pulley is secured to a sturdy timber frame high above. A rope is threaded through its groove, one end tied securely to the stone, the other end held by a team of workers on the ground. Before the pulley, they would have to pull upward, a straining, awkward motion with limited power. But with that wheel in place, they simply pull down. They lean back, planting their feet and using their full body weight against the rope. The pulley smoothly redirects their downward effort, and the stone rises straight up. This shift from pulling up to pulling down was revolutionary. It was safer, allowing for better footing and coordination. It was more efficient, letting workers use gravity to aid their own strength. And it granted exquisite precision, enabling tiny adjustments as the stone neared its final position. These early single pulleys, carved from wood or even stone, did not yet multiply force like the compound systems that would come later. Their genius was in transformation, turning a horizontal tug into a vertical lift. This principle became the heart of the earliest cranes, simple derricks that used a pulley to guide blocks into tight spaces where a ramp could not reach. It was the final piece of the toolkit, a way to command the last critical feat of a stone's journey. With the pulley, the ancient builders' command over weight and motion was complete, from the first shove to the final, gentle placement. Yet for all these brilliant machines, one question echoes from the silent quarries and empty deserts. How did they coordinate it all? How did these principles assemble into a symphony of movement that could build a civilization? The true power of these tools was not in their isolation, but in their orchestration. To move a mountain, you need a symphony, not a solo. This orchestration reached its zenith in the systematic management of friction on a grand scale, a principle perfectly embodied by the Sled and the Slipway. Picture a colossal stone statue, perhaps one of the famous Moai of Easter Island, standing several stories tall and weighing dozens of tons. To move it from the quarry to its coastal platform, brute dragging would be futile. The statue would simply dig itself a grave in the soft earth. The solution was a masterful two-part system. First, the statue was carefully lowered onto a large, sturdy wooden sled, a platform that distributed its immense point load over a much wider area. This alone prevented the stone from sinking, but the sled itself would then seize against the ground, creating a new point of friction. So came the second part, the prepared pathway. Workers would create a track, a slipway, leading precisely to the destination. This was not just any path, it was an engineered surface. In some cases, it was packed earth smoothed to perfection. In others, it was smeared with a slick mixture of wet clay, silt, or even animal fat. This lubrication transformed the ground from a gripping surface into a near frictionless plane. Now, when teams pulled on ropes lashed to the sled, the entire assembly would glide forward with a surprising smoothness. The sled bore the weight, the slipway defeated the friction, and the coordinated pull of the workforce provided the steady, manageable force. This method was not unique to the Pacific. It echoes in the movement of Egypt's own colossal statues. A prepared track, sometimes even fitted with wooden rails to guide the sled's runners, turned chaotic, exhausting dragging into a controlled, repeatable, and almost industrial process. It was friction management systematized, a testament to the ancient understanding that the greatest obstacles are overcome not by fighting nature head-on, but by cleverly reshaping the interface between the object and the world. Even the most coordinated human team faced a ceiling of strength, a limit to the sheer pulling force they could generate. To move beyond it, ancient builders looked to a new class of allies, creatures whose power could be systematically multiplied. They turned to the might of domesticated animals, transforming oxen, donkeys, and in certain regions, elephants, into living engines of traction. This was a strategic leap from human muscle to organized animal logistics. The principle was straightforward but profound. By yoking multiple teams of animals to a single massive sled or sledge, the available pulling force could be increased exponentially. One ox might pull with the strength of several men, but a paired team, perfectly synchronized, could pull far more than twice that, their combined power focused into a single, steady draw. The true engineering challenge, however, was not in the animal's strength but in their coordination. A disorganized pull was worse than useless. It risked tangling lines and wasting energy. Skilled drivers and overseers became essential, using specific calls, whip cracks, or gestures to command all animals to lean into their harnesses at the exact same moment. This orchestrated unison turned a chaotic crowd of beasts into a single, pulsing machine of force, maximizing every ounce of their collective power. This integration was crucial for the grandest infrastructure projects. Imagine the construction of a Roman road, where teams of oxen dragged heavy stone blocks for miles to create a stable foundation. Or consider the transport of pristine white marble from the quarries of Mount Pentelicus to the Acropolis in Athens, a journey where animal power made the vision of the Parthenon physically possible. Harnessing this power required its own suite of innovations, an early form of interdisciplinary engineering. Builders had to understand traction, designing harnesses that distributed pressure across an animal's body without causing injury or restricting breath. They needed to comprehend animal behavior, knowing how to motivate and calm their living machines. This was never about mere brute force. It was about channeling and amplifying a natural power through intelligent design and precise command. The rope, the yoke, and the driver's signal became tools as vital as the lever or the ramp. extending human will through the disciplined strength of another species. Yet for all this amplified power, the most elegant solutions often came from a quieter understanding, a way to make the load itself cooperate with the journey. The greatest danger when moving a stone was not its weight, but its potential to move too fast. An uncontrolled descent could shatter months of work in an instant, or worse. To master gravity itself, ancient builders learned to balance it, using one heavy object to control the fate of another. This was the principle of the counterweight, a shift from raw force application to the elegant management of energy. Picture a deep tomb shaft, its entrance a perfect square cut into the desert floor. A multi-ton granite slab, the final seal for the chamber below, needs to be lowered with absolute precision. A direct drop is unthinkable. It would crack the stone and damage the shaft. So a timber frame is erected over the opening, with a strong horizontal beam acting as a pivot at its peak. Ropes are attached to the sarcophagus lid, running up and over the pivot, but on the other side of that pivot, hanging in open air, is not an empty rope, but a carefully calculated mass of stone blocks bundled together. This bundle is the counterweight. Its mass is chosen to be just slightly less than the weight of the granite lid. When workers release the brake mechanism, the heavier lid begins to descend, but it does not fall. It is gently, irresistibly pulled down by the rising counterweight on the opposite side. The system finds a near equilibrium, a slow and graceful exchange of positions. The workers now have total control, with only a modest additional push or a light brake needed to guide the final inches of the descent. This was force management in its purest form, turning the dangerous power of gravity into a predictable, safe partner. We see echoes of this balancing act in simpler technologies, like the shadoof, an ancient irrigation device where a bucket of water is lifted from a river by the downward pull of a clay weight on a lever's other end. The same fundamental idea would later reach its zenith in the great cranes of medieval cathedrals, where human-powered treadwheels acted as massive, adjustable counterweights to lift Gothic stones hundreds of feet into the air. The counterweight did not just move objects, it domesticated gravity, introducing a new language of stability and safety to the conversation between human ambition and immovable mass. Precision is the silent partner to power. A stone might be floated down a river and hauled up a ramp, but if it does not settle into a perfect, seamless fit, the entire endeavor crumbles into a chaotic pile. This is where ancient engineering transcended mere movement and entered the realm of geometry, a meticulous dance of measurement and alignment that turned colossal construction into a precise art. The tools for this final act of perfection were deceptively simple, yet they harnessed fundamental laws of nature with unwavering accuracy. Take the Plumb bob, nothing more than a symmetrical weight, often of stone or metal, suspended from a cord. When held still, gravity pulls that weight into a perfectly vertical line, an absolute reference to the center of the earth. A builder could hold this device against the rising edge of a stone wall, and by observing the gap between the cord and the masonry, correct any lean, inch by careful inch, until the wall stood true. For the horizontal plane, they turned to another elemental force, water. A water level was simply a shallow, straight trough filled with liquid. Because water always seeks its own level, the surface in the trough created a flawless horizontal line, a local horizon that was identical at both ends of the stone being set. By placing a marker at the water's edge on one end and sighting across to the other, they could ensure a block was laid perfectly flat, preventing any unsettling tilt that would compound into disaster higher up. These were not just tools, they were applications of physics, gravity, and hydrostatics transformed into practical guides for human hands. This obsessive geometric accuracy is what gives ancient sites their breathtaking authority. The famous Inca stonework of Machu Picchu, where massive, irregularly shaped blocks fit together so tightly that a knife blade cannot be inserted between them, speaks to a culture that mastered this art of measurement. It was not magic, it was a relentless process of trial, adjustment, and verification using these basic instruments. Similarly, the astronomical alignments of monuments like Stonehenge or the Great Pyramid required this same precision on a monumental scale. To ensure a temple doorway framed the rising sun on the equinox, or a corridor pointed precisely at a northern star, builders used measuring cords, sighting poles, and the steady reference of their plumb lines to transfer celestial geometry onto the dusty earth. This meticulous attention to the final, static placement reveals the complete picture of their genius. They understood that moving a mountain was only half the task. The true goal was to make that mountain stand forever, aligned with the cosmos and bonded by seams so perfect they seemed grown, not built. But physics alone could not lift a single block. The equations of levers and friction required a final, living component to solve them: the organized human body. The most sophisticated machine in any ancient quarry was not made of wood or stone, but of flesh, bone, and shared intention. By orchestrating thousands of laborers into perfectly synchronized teams, engineers created a living engine, a system where social physics amplified brute strength into a directed, unstoppable force. This was engineering applied to people, transforming the chaos of a crowd into the precision of a mechanism. Imagine the scene at the base of a pyramid ramp. A colossal block rests on a lubricated sled, ropes fanning out from its front like reins. Along each rope, not a disorganized mob, but ranks of workers arranged in precise columns. An overseer stands to the side, not with a whip, but with a simple drum or a rhythmic chant. He calls out a beat, a steady 1-2, 1-2. On the first beat, every worker braces, planting their feet and gripping the rope. On the second beat, they lean back in a single, fluid motion, their combined weight translating into a unified tug. The sled inches forward, rest, reset, pull again. This rhythmic coordination was everything. If one team pulled out of sync, their force would fight against the others, creating a wasteful internal conflict. But in perfect unison, their individual efforts summed into a smooth, continuous pull far greater than their number. It was the human equivalent of pistons firing in an engine, each small stroke contributing to a powerful, regular output. Ancient art and texts from Egypt to Mesopotamia show these scenes, depicting lines of pullers moving as one under the guidance of a timekeeper. This was more than just hard labor, it was a cognitive leap. It required understanding group psychology, motivation, and fatigue management. Engineers devised shift patterns, ensuring fresh teams rotated in to maintain constant momentum. They provided sustenance and organized shelter, recognizing that the machine's efficiency depended on the well-being of its human parts. This social engineering turned the abstract physics of mechanical advantage into a tangible, earth-moving reality. The true foundation of every ancient wonder was this profound understanding that to move mountains, you first had to harmonize the multitude. The rhythm of the drum coordinated the pullers, but could its sound have done more than simply set the pace? There exists a fascinating and speculative frontier in this story, where the physics of movement meets the physics of sound. Some researchers and theorists propose that ancient builders might have understood something profound about vibration, using rhythmic sound not just to organize people, but to directly influence the materials themselves. The idea suggests that specific resonant frequencies, produced by chanting, drumming, or even primitive musical instruments, could have been employed to reduce friction or make massive stones somehow easier to handle. While this remains outside mainstream archaeological consensus, it opens a captivating window into a different kind of ancient knowledge. Modern experiments have shown something curious, that sound waves at certain frequencies can dramatically alter the behavior of granular materials like sand or gravel. Under the right vibration, these particles can begin to flow almost like a liquid, a state known as liquefaction. Imagine a stone sled poised on a track of desert sand. If teams generated a powerful, unified rhythm through pounding drums or deep, resonant chanting, the vibrations traveling through the ground might have temporarily transformed the sand beneath the runners. That gritty, gripping surface could become a fluid, slippery plane, drastically cutting the drag. The stone would not truly weigh less, but the resistance against it could momentarily vanish. This is not magic, but an applied, if intuitive, understanding of wave physics. It speaks to a potential harmony between ritual and engineering, where the sensory environment, the very air and earth, became a tool. The rhythmic work songs we often picture may have served a dual purpose, aligning human muscle while simultaneously conditioning the path ahead. This speculative concept reminds us that ancient techniques were born from deep, sustained observation of the natural world, encompassing phenomena we are still learning to measure today. It sits at a beautiful intersection where the coordination of bodies might have extended into a coordination with the environment itself, using sound to persuade the earth to cooperate for one monumental task. Granite obelisks stand as perhaps the purest test of ancient engineering principles. To raise a single one, a slender monolith often exceeding 300 tons, required not just one clever trick but a flawless sequence of them, a complete symphony of simple physics performed on a colossal stage. The entire process, from the quarry to the final, upright stance, was a masterclass in applied logic, each phase solving a specific problem with the tools we have explored. It began deep within the bedrock of Aswan, where workers carved trenches around a chosen block of pristine red granite. To free it from the living stone, they did not cut it with saws, but persuaded the rock to split itself. They carved a line of holes along the desired fracture line, then hammered dried wooden wedges into each one. Next, they poured water over the wedges. The wood swelled with tremendous, relentless force, a power generated by the simple absorption of moisture. This expansion, channeled by the precise holes, created a clean, controlled fracture, shearing the obelisk free from the quarry floor with a sound that must have echoed like thunder. Once liberated, the real work of movement began. The monolith was carefully lowered onto a massive, reinforced wooden sled. A prepared slipway, likely lubricated with a slick slurry of Nile silt and water, led from the quarry to the riverbank. Teams of laborers, coordinated by rhythmic calls, would haul this incredible load, its runners gliding over the slick track, turning the impossible drag into a managed, incremental slide toward the water. This was friction management on an epic scale, the sled and slipway in perfect harmony. At the river's edge awaited a barge of staggering size, a vessel built specifically for this one task, perhaps constructed around the obelisk itself. Using ramps and levers, the stone was transferred onto this floating platform. The genius of flotation then took over. On the water, the effective weight of the obelisk was cut nearly in half, allowing teams of rowers to tow the barge hundreds of miles down the Nile with relative ease. The river, the world's smoothest highway, carried the weight. Upon reaching its sacred destination, the obelisk faced its greatest trial, the transition from horizontal to vertical. A vast earthen ramp was built, rising at a shallow angle to meet the top of the waiting pedestal. The sled bearing the obelisk was dragged up this incline until the stone's base hung precisely over the deep foundation hole. Now came the moment of breathtaking precision. The base of the obelisk was pivoted into a prepared socket at the ramp's edge. Slowly, controllably, the far end of the stone was lowered, perhaps by gradually releasing ropes or by letting sand drain from compartments built beneath the sled. As the granite needle descended, its base settled into the hole, guided by the sloping sides of the ramp. The sand provided a controllable, granular break, allowing for minute adjustments until the obelisk stood true. Finally, the ramp was dismantled, leaving the stone standing alone, a testament not to magic but to method. Every principle we have discussed, the lever, the inclined plane, the roller, flotation, and friction control, was present in this single, magnificent operation. It was the ancient engineer's ultimate proof of concept, demonstrating that with a deep understanding of simple physics and impeccable coordination, humanity could make the Earth itself obey a grand and graceful design. This orchestration of sound and motion, however speculative, meets its most tangible test not in the desert but on the damp, rolling grasslands of prehistoric Britain. Here stands Stonehenge, a ring of silent giants whose journey defies simple explanation. The central mystery is not the purpose of the circle, but the sheer physical feat of its assembly. The largest of its Sarsen stones, towering pillars of dense sandstone, each weigh around 25 tons, equivalent to 5 adult elephants. Their quarry lies 20 miles to the north, across a landscape of forests, gentle hills, and soft, waterlogged ground. Moving a single one of these megaliths that distance without the wheel, without metal tools, and without draft animals on the scale of oxen, represents one of history's most profound logistical puzzles. The solution almost certainly lay in a masterful adaptation of the very principles we have traced, tailored to a very different world. It was a slow-motion ballet of wood, rope, and human will, transforming an epic trek into a repeatable, almost industrial process. The journey began not with a pull, but with a preparation of the path. Researchers now believe the builders likely constructed a trackway, a temporary but engineered road for the stones to travel. This was not a paved highway, but a prepared surface designed to conquer the inconsistent, yielding earth. In some areas, this may have been a compacted walkway of crushed chalk and soil, hardened by countless footsteps. In others, especially across boggy ground, it might have involved laying down a corridor of wooden planks or split logs, creating a firm, continuous surface. This trackway served a critical dual purpose. First, it distributed the immense point load of the stone, preventing the sledge from sinking catastrophically into soft earth. Second, and just as importantly, it provided a consistent interface for the next key innovation, the lubricated rail. Imagine the scene. A colossal Sarsen stone is securely lashed to a massive wooden sledge, a platform built from mighty oak trunks. But this sledge does not run directly on the trackway. Instead, it rests upon a set of parallel timber rails, greased with animal fat or perhaps a paste of wet clay. This simple addition changes everything. The friction is now between the smooth, greased rail and the smooth runner of the sledge, a pairing designed for minimal resistance. The rails themselves, laid end to end along the prepared track, guide the load in a straight line and prevent lateral shifting. A team of perhaps 100 or more people, harnessed to long hemp ropes, would take the strain. At a coordinated signal, they would lean into their walk, not a frantic sprint but a steady, plodding march. The sledge would glide forward on its greased rails, inching along its artificial highway. As the stone advanced, workers at the rear would retrieve the now uncovered rails and rush them to the front, laying them down again for the next segment of the journey. This recycling of the rail track, much like the rollers used elsewhere, meant the stones carried their own pathway with them, piece by piece. This method transforms the seemingly impossible into the arduously achievable. Experiments by archaeologists and engineers have demonstrated its startling efficiency. A dedicated team, using a replica sledge on greased timber rails, can move a 25-ton stone at a pace of roughly 1 mile every 10 days. While slow, this pace is steady, controlled, and sustainable. It turns a monumental mystery into a matter of meticulous logistics, of organizing labor, maintaining the trackway, and ensuring a steady supply of grease and timber. The 20-mile journey for a single Sarsen might have taken a season, a communal effort woven into the annual rhythm of life. It highlights an engineering mindset focused not on a single flash of genius, but on systematic problem solving. They adapted the universal principles of reducing friction and distributing weight to the specific challenges of their own landscape, using the materials they had in abundance: wood, rope, and determined communal effort. The silent stones of Salisbury Plain, therefore, are not just monuments to belief, but to a deep, practical intelligence, a testament to what simple physics and human coordination can transport across the very face of the earth. This same principle of controlled motion finds its most dramatic and almost mythical expression on a remote island in the Pacific. Easter Island, or Rapa Nui, is home to the silent, enigmatic Moai, those towering stone faces gazing inland from their coastal platforms. For centuries, their very presence posed a riddle. How did a society with no metal, no wheels, and no large animals move nearly 900 of these multi-ton statues, some as tall as 3-story buildings, across miles of rugged terrain from the quarry to the coast? The answer, emerging from both local oral history and modern experimental archaeology, is as elegant as it is audacious. They made the statues walk. This was not a metaphor, but a literal technique, a breathtaking dance of physics and human coordination. The method relied on a profound intuitive grasp of the statue's own structure. Each Moai is not just a block, it has a distinct, elongated shape with a low, heavy base and a high center of gravity, much like a person standing upright. This shape is the key to its movement. The process likely began with the statue already standing upright on a prepared base at the quarry. Teams would attach 2 strong ropes to the top of the Moai, one on each side. Then, in a rhythmic, rocking cadence, they would begin to pull. The team on one side would pull their rope with a coordinated heave, tilting the statue onto its opposite corner. Just as the statue reached the peak of its tilt, that team would ease their pull, and the team on the opposite side would pull their rope, swinging the giant forward and onto its other corner. With each rhythmic pull and release, the statue would rock from side to side, pivoting on its base, and with each rock, it would lurch forward a few inches. From a distance, it would appear as if the colossal stone figure was walking itself across the landscape, swaying with a slow, deliberate gait. This technique is a masterful application of rotational dynamics and pendulum-like motion. The pullers were not dragging dead weight, they were harnessing the statue's own mass and momentum, using its high center of gravity to create a controlled, falling swing. The timing had to be perfect. A fraction of a second off could send the Moai toppling into an irreparable crash. It required not just strength, but a deep, shared rhythm and an intimate feel for the stone's balance. This walking method explains peculiar features found on some Moai discovered along the ancient roads. Their bases are often rounded and worn on the front edges, consistent with a rocking, pivoting motion, not a flat drag. It also aligns powerfully with the islanders' own ancestral stories, which have long spoken of the statues walking with mana, or spiritual power, guided by the chiefs. What was once seen as pure legend now reveals itself as a cultural memory of an ingenious engineering practice. The Moai walkers demonstrate the ultimate refinement of our theme. They turn the object's greatest challenge, its immense and precarious weight, into the very engine of its movement. They did not fight the stone's mass, they conversed with it, persuading gravity itself to become a partner in the journey. The Moai did not walk on the first attempt. That perfect, rhythmic sway was not an idea plucked from thin air, but a hard-won truth carved from countless failures. This is the hidden foundation beneath every technique we have seen, a bedrock of empirical knowledge built not from theory, but from relentless, hands-on trial and error. Those early engineers were the ultimate pragmatists. They did not have textbooks on coefficient of friction or tensile strength. Instead, they had generations of watching, testing, and learning from what worked and, more importantly, from what broke. They discovered which type of timber, perhaps oak for its resilience or cedar for its straight grain, could bear the tremendous stress of a lever without splintering under a multi-ton load. They learned through experience which mixture for their slipway, a blend of particular Nile clay versus desert silt, created the most effective, long-lasting lubricant. They determined the optimal slope for a ramp not by calculation, but by observation, seeing how a slightly steeper angle exhausted their teams too quickly, while a gentler one made the journey impractically long. This was knowledge written in calloused hands and remembered in shared stories, a living database of cause and effect. The master builder knew because his teacher knew, because someone long ago had tried a different way and watched a rope snap or a sled buckle. This process of iterative refinement is the unsung hero of ancient innovation. Each project was a massive experiment, and success was a set of reproducible steps that could be taught to an apprentice. The apprentice would then add his own observations, perhaps noting that a rope soaked in water held a knot better, or that pulling at dawn when the air was cool prevented heat exhaustion in the teams. This slow, cumulative accretion of practical wisdom was the cutting-edge technology of its era. It underscores a profound truth about human progress, that the formal scientific method, with its hypotheses and controlled experiments, is simply a structured version of what these builders did instinctively. They observed a problem, they proposed a solution based on past experience, they tested it at a colossal scale, and they carefully noted the results. Their legacy is a testament to the raw power of focused observation and relentless problem-solving, proving that the path to moving mountains is paved with the lessons of 1,000 smaller stones. The true genius of these methods was their profound flexibility. There was no universal blueprint shipped from some ancient engineering headquarters, because the most critical component of every project was not imported. It was already there under their feet and in the surrounding landscape. The principles of physics were constant, but their application was a brilliant, localized improvisation, a dialogue between human need and environmental possibility. In the dense, old-growth forests of northern Europe, timber was the ultimate resource. The very challenge of moving a stone through a wooded landscape provided its own solution, an endless supply of straight, strong trunks for rollers, levers, sledges, and trackways. The forest itself became the toolkit. Contrast this with the sun-baked river valleys of Egypt. Here, vast forests were a dream, but the desert offered other gifts: fine silt from the annual Nile flood, clay, and limitless sand. So they engineered with earth, mixing mud and water into perfect lubricants for their slipways, and packing the very desert soil into the colossal ramps that became temporary mountains. Their primary building material and their primary tool for moving it were often one and the same: the ground they stood on. This resourcefulness extended to the very paths they traveled. Coastal and riverine cultures, from the Polynesian islands to the banks of the Nile, saw water not as a barrier but as a pre-made transportation grid. They invested their skill in boat building and buoyancy, letting the fluid medium carry the load. Meanwhile, in the rugged highlands of the Andes, where steep slopes and seismic activity were constant facts of life, engineers developed a mastery of terracing and precise stone fitting. Their movement was often less about long-distance transport and more about ingenious pivoting and balancing, using gravity and interlocking geometry to make structures hold fast against the mountain's shake. This contextual intelligence reveals the deepest layer of their understanding. They did not see the environment as an obstacle to be conquered with foreign technology, but as a partner offering specific, available answers. It was a sustainable, low-tech philosophy born of necessity. By working with what was locally abundant, they minimized waste and energy expenditure, creating solutions that were elegantly integrated into their ecosystem. The lesson echoes across millennia. The most enduring engineering often starts not with what you wish you had, but with a deep, observant respect for what you already do. The silent, rhythmic pull of the ropes was powered by something deeper than muscle. For a society to commit generations to a single, staggering task, the motivation had to be more profound than a simple command. The stones themselves were not just weight, they were meaning. This is where the story transcends physics and enters the realm of the human spirit. The cultural or religious significance of these monuments provided an invisible yet essential form of energy. When labor is framed as a sacred duty, a direct service to the gods or a conduit to the ancestors, the very nature of the work transforms. Dragging a stone for a temple becomes an act of devotion. Carving a moai is not just shaping rock, it is anchoring the protective gaze of a chief's spirit to the community. This belief system turned exhausting, dangerous toil into a purposeful pilgrimage, a shared endeavor that wove individual effort into the grand tapestry of cosmic order. The promise was not of wages but of divine favor, communal prestige, or eternal legacy. This psychological foundation made the impossible seem not only achievable but necessary. It was the fuel that sustained the fire of effort across decades, even centuries. The master builders and the spiritual leaders were likely partners in this endeavor. While engineers solved the equations of leverage and friction, priests and overseers managed the equally complex equation of human will. Ceremonies at the quarry, blessings of the first block, festivals marking the completion of a course, all these rituals renewed the collective spirit. They broke the monotony of the task into sacred chapters, offering moments of celebration and reaffirmation of the shared goal. This management of morale was a critical, intangible technology. It prevented the project from collapsing under the weight of its own scale by constantly reminding every participant of the why. The rhythmic work songs were not just for timing, they were for unity, weaving individual voices into a single chorus of purpose. The communal feasts after a milestone provided not just nourishment, but a tangible reward and a reminder of the social bond. This psychological engineering addressed the most fragile component in the entire system, the human heart. It transformed a workforce from a collection of individuals into a single, determined organism with a unified will. The true monument, then, was not just the finished pyramid or circle of stones. It was the collective belief that built it, a testament to the fact that the most complex force to channel in any great undertaking is not gravity or friction, but the enduring power of a shared idea. Yet for every towering success, there were silent lessons carved into the desert floor. Scattered across the ancient world, we find the other side of the story. Quarries holding half-freed obelisks, massive blocks cracked and abandoned, the ghostly outlines of ramps that gave way. These sites of failure are not evidence of ignorance, but of its opposite. They are the physical records of experimentation, the necessary cost of pushing against absolute limits. Each broken stone was a brutal but unambiguous teacher. A granite lever that snapped under the strain of a multi-ton pivot taught a visceral lesson about the tensile strength of wood, informing the selection of heartier timber or the design of a thicker, reinforced beam for the next attempt. A ramp of packed earth that slumped and collapsed under the constant traffic of sleds provided critical data on slope stability and soil compaction, leading to better techniques for layering and watering the earth to create a more durable incline. These were not merely accidents, they were field experiments on a colossal scale, where the results were written in landslides and fractures. Studying these abandoned efforts completes the human picture, stripping away any illusion of infallible ancient wisdom. It reveals a process defined by risk, setback, and hard-won incremental improvement. The master builder's true skill was not just in applying known principles, but in diagnosing failure, adapting, and persevering. Acknowledging these limits does not diminish their achievements, it grounds our admiration in a more profound reality. It highlights the resilience and relentless problem-solving required to transform a catastrophic collapse into nothing more than a temporary delay on the path to eternity. Their legacy is not one of perfect first tries, but of a stubborn refusal to let the lesson of a broken stone be the final word. The echoes of those ancient rhythms are not lost to history. They resonate in the steel and hydraulics of our modern world. The same principles that guided a stone up a mud ramp are embedded in the DNA of every construction crane and heavy hauler working today. This is not a coincidence, but a direct legacy, a continuous thread of applied physics woven through millennia. Take the modern crane, that iconic silhouette against the city skyline. At its heart, it is not a new invention, but the ultimate evolution of the simple pulley and lever. Where ancient builders used a single wooden wheel to redirect force, a tower crane employs a complex system of multiple sheaves, or pulley wheels, creating a compound mechanical advantage so powerful that a single motor can hoist loads of several tons hundreds of feet into the air. The principle of trading distance for force is identical, only the materials and the power source have changed. Similarly, the hydraulic jack has become our contemporary lever. Instead of a timber beam pivoting on a stone, it uses the incompressible nature of fluid. A small force applied to a piston in a confined chamber of oil creates pressure, which is then transmitted to a much larger piston, multiplying the force to lift a car or level a building foundation. It is the same concept of amplified force, but achieved through fluid pressure rather than a rigid beam. Even the most advanced heavy load transporters, the multi-wheeled platforms that move rocket boosters or reactor cores, are direct descendants of the sled and roller. They use precisely engineered, independently rotating wheels and low-friction polymer bearings to distribute weight and minimize resistance, executing the ancient mandate of friction management with computer-aided precision. The fundamental physics, the relentless pursuit of mechanical advantage and controlled motion, remains the universal language of engineering. This legacy is more than historical curiosity. It is a source of inspiration. Modern engineers facing challenges of sustainability and energy efficiency sometimes look back to these ancient, low-energy solutions. The elegance of a counterweight system, the simplicity of a prepared slipway, or the communal efficiency of coordinated human power can spark ideas for contemporary problems, reminding us that the most brilliant solutions are often rooted in the timeless logic of the physical world. Our ancestors were not primitive, they were pioneering practical physicists, and their silent stone textbooks continue to inform the structures we build today. The greatest mystery is not how they moved the stones, but why we so often refuse to believe they could. When faced with the staggering scale of these ancient works, a tempting narrative emerges, one that credits extraterrestrial visitors or a lost super-civilization with advanced technology. These stories are captivating, but they carry a subtle and profound disservice. In seeking to explain the inexplicable, they inadvertently rob our own ancestors of their rightful genius. The implication is that ordinary humans with nothing but time, observation, and determination could not possibly have achieved such wonders. This perspective overlooks the most compelling evidence of all, the fact that we have done it ourselves again and again, using nothing but the very methods we have explored. Archaeologists and engineers around the world have conducted remarkable experiments, putting these ancient techniques to the ultimate test. They have carved multi-ton blocks from quarries using only stone tools and swelling wood. They have built sledges from hand-hewn timber, lubricated slipways with clay and water, and organized teams of volunteers to pull colossal weights. In one famous project, researchers successfully walked a full-size replica Moai across Easter Island terrain using nothing but ropes and coordinated rocking. In another, teams using period-appropriate levers, rollers, and earthen ramps have quarried, transported, and raised multi-ton blocks to construct accurate, small-scale pyramids. These are not thought experiments, they are physical, dusty, exhausting proofs of concept. Every groan of the rope, every inch gained by the stone, echoes the efforts of those ancient builders. The results are clear. The principles of simple physics, when combined with organized human intelligence and immense patience, are not just sufficient, they are the only explanation required. Debunking the myth of alien intervention, then, is not an act of dismissing wonder. It is the opposite. It is about reclaiming that wonder and directing it to its true and far more inspiring source, the incredible capacity of human creativity and perseverance. It asks us to see these monuments not as gifts from the stars, but as triumphs of the human spirit here on Earth, a testament to what we can achieve when a community aligns itself with a single, seemingly impossible purpose across generations. The real lost knowledge is not some advanced technology, but the profound understanding that our greatest tool has always been each other. The master builder's role was not that of a specialist, but of a grand synthesizer. To command a stone from quarry to pinnacle required a mind fluent in many languages, not of words, but of stars, stone, soil, and stream. This was ancient engineering in its truest form, a profoundly interdisciplinary endeavor long before the term existed. The project began not with a blueprint, but with a conversation between the engineer and the astronomer. To align a temple corridor with the rising sun on the solstice, or a pyramid's base with cardinal directions, the engineer needed precise celestial data. This knowledge dictated the monument's orientation, turning the entire construction into a massive, permanent astronomical instrument. Simultaneously, the engineer consulted with those who understood the Earth itself, individuals with a deep, practical geology. Selecting the right quarry was a science. They sought stone not just for its beauty, but for its integrity, its grain, its ability to be worked and to withstand immense pressure. They could read the landscape, identifying seams and fracture lines in the bedrock that would allow a clean break. This was applied earth science, ensuring the raw material was worthy of the journey it would undertake. Once the stone was chosen, another expert's knowledge became vital, that of the botanist or master woodsman. The success of levers, sledges, and rollers depended entirely on the properties of wood. Which tree offered the perfect combination of strength, straightness, and resilience? Oak for its unyielding toughness, perhaps, or cedar for its resistance to rot, and its long, straight trunks ideal for rollers. This was material science drawn from the living forest, and for transport, the hydrologist's insight was paramount. Understanding the Nile's annual flood cycle, its currents, and its depths was essential for planning the flotation of obelisks. Knowing how to divert a small stream to lubricate a slipway, or where the water table was high enough to help float a stone across a swamp, turned a basic element into a powerful tool. The chief engineer stood at the center of this web of knowledge. He was the ultimate systems thinker, integrating celestial maps, geological surveys, botanical catalogs, and hydrological charts into a single, executable plan. His genius lay in seeing the connections, in understanding how the phase of the moon might affect the river's height for a barge launch, or how the seasonal hardness of a particular wood would bear on a lever's design. This holistic approach is a powerful mirror to our own modern world, where the most complex challenges, from climate science to space exploration, are solved not in isolated silos, but at the vibrant intersections of disciplines. The ancient builders left us a lesson etched in stone, that to move the heaviest objects or to solve the most weighty problems, we must first learn to connect all the pieces of the world we see. Numbers can transform awe into understanding. Consider the simple physics of a single pyramid block, a limestone cube weighing around 2.5 tons. On a level surface, moving it would demand a Herculean effort. But place that same block on a sled atop a lubricated ramp with a gentle slope, and the required pulling force plummets. Experimental archaeology suggests a team of perhaps 20 men, harnessed to ropes and moving in perfect rhythm, could provide the steady, manageable force needed to drag that block upward. The inclined plane does its silent work, trading the brutal vertical lift for a long, patient horizontal pull. Now multiply that single action. The Great Pyramid is composed of roughly 2.3 million such blocks. The arithmetic becomes almost incomprehensible. Moving just one block represents a coordinated effort, a tiny unit of labor we can call a man-day. To move millions, you are talking about millions upon millions of man-days of focused work. When historians and engineers run these calculations, factoring in quarrying, transport, shaping, and placement, the figures point to a workforce of several thousand people laboring not for a season, but for decades. This shifts our perspective from the stone to the society behind it. A project of this magnitude required more than brilliant engineering. It demanded a breathtaking feat of social organization. It meant feeding, housing, and managing a small city of workers year after year. It required administrators to coordinate the supply chains, bringing food from farms, water from the Nile, and copper tools from distant mines. It involved planners who thought not in weeks or months, but in generations, orchestrating a vision that would outlive everyone who broke ground on the first course. This long-term commitment reveals a civilization operating at the peak of its collective capacity. The true resource being allocated was not just stone or muscle, but time itself on a scale that staggers the modern mind. To dedicate such a vast portion of a society's energy and lifespan to a single, non-utilitarian goal speaks to a shared purpose that transcended the individual. The monument they built is in essence a frozen ledger of that societal effort, a mountain that quantifies the belief, the coordination, and the patient will of an entire culture. It stands as proof that humanity's greatest constructions are always at their core, a measure of what we can achieve together. Granular materials held a quiet power in the ancient builders' hands. Sand and gravel were not just debris to be cleared away. They were active, controllable components of the engineering process, a kind of liquid solid that could be persuaded to do precise work. This understanding of granular physics, the behavior of countless small particles acting together, gave them a tool of beautiful versatility. For foundational work, achieving a perfectly level base on uneven ground was a constant challenge. Their solution was both simple and brilliant. They would dig a network of shallow trenches across the building site, crisscrossing the area like a grid. Then they would pour dry sand into these trenches until it was perfectly level with the top. Sand, when dry and loose, cannot form a slope on its own. It naturally seeks a flat, even surface. By using the trench edges as a guide and carefully smoothing the sand, they created a flawless horizontal plane, a reference surface born from the self-leveling nature of the material itself. On this perfect sandy canvas, they could then lay their first course of stones with absolute confidence, knowing the entire massive structure would rise from a true and steady base. The sand did the measuring for them, turning a complex geometric problem into an act of careful pouring. But sand's role was not just static, it could also be harnessed for controlled motion. Imagine the final lowering of a massive lintel stone onto two waiting pillars. A direct drop was out of the question. The stone would shatter or miss its mark. So builders constructed a temporary wooden box or compartment directly on top of the pillars, right where the stone needed to sit. They filled this box completely with dry sand. The stone was then carefully maneuvered above it and set to rest on the sand-filled container. Now came the moment of exquisite control. Workers would open small, plugged holes in the sides of the wooden box. The sand began to drain out slowly, steadily. As the volume of sand decreased, the massive stone above would descend, millimeter by patient millimeter, settling downward as the supporting medium literally flowed out from under it. This allowed for adjustments so fine they could use a feather to check the final fit. It was a brake system made from earth itself, transforming a dangerous fall into a graceful, manageable descent. Similarly, gravel beds served a vital purpose in the grander transport schemes. A slipway built directly on soft, wet ground would quickly become a muddy, unusable trench. By laying down a deep bed of compacted gravel first, builders created a stable, well-draining foundation. The gravel distributed the immense point load of the sled, prevented water from pooling and turning the path to muck, and provided a firm, consistent surface for the lubricated rails or runners to glide upon. These everyday materials, so often underfoot, were in fact sophisticated tools. Their predictable behavior under pressure and flow made them ideal for tasks requiring both stability and adjustability. The ancient mastery of sand and gravel reveals a nuanced observation of the physical world, where even the ground beneath their feet could be choreographed into the silent, supporting cast of their monumental ambitions. The ingenuity we have traced casts a long and brilliant shadow, but within that shadow lie other truths, ones that complete the picture in a more sobering light. For all the elegance of the lever and the cleverness of the ramp, the true engine behind many of these wonders was not just physics, but people, often under conditions of immense hardship. The stones did not move themselves, and the coordination of thousands required more than shared purpose. It frequently rested upon systems of profound inequality, from corvée labor, where citizens were compelled to work for the state, to outright slavery. This is the complex duality at the heart of these monuments, a testament to human intellect built upon a foundation of human cost. To understand them fully is to hold both realities in mind, to see the soaring triumph of engineering while acknowledging the societal structures that made such concentrated effort possible. The Great Pyramid, for instance, was likely constructed not by slaves in chains as once popularly believed, but by a rotating workforce of skilled laborers and conscripted farmers working during the Nile's flood season when fields were idle. Yet this does not erase the element of coercion, the reality of a social order where the will of the divine pharaoh commanded the labor of thousands as a form of tax or duty. Their ingenuity in logistics extended to managing this human resource, providing bread, beer, and housing to sustain the workforce, but within a framework where individual choice was severely limited. This context does not diminish the technical achievement, but it deepens our historical understanding. It reminds us that these structures are not just feats of engineering, but also mirrors of the societies that built them, reflecting both their soaring aspirations and their entrenched hierarchies. The legacy, therefore, is necessarily mixed. We can stand in awe of the precise geometry, the mastered physics, the breathtaking scale, while also recognizing that such concentrated effort was often enabled by power structures that would be unthinkable today. This critical awareness allows for a more complete, more human appreciation. It transforms a monument from a sterile puzzle of ancient technology into a deeply human document, a record of both brilliant minds and the complex, often difficult, circumstances of their time. The silent stones, then, tell two intertwined stories, one of a culture's pinnacle of creative problem-solving, and another of the social realities that provided the immense, directed energy required. To listen to both is to engage with history in its full, challenging, and resonant depth. From the ramps of Giza to the rocking Moai, this entire story is a testament to something fundamental within us, an innate ability to observe the world and ask a simple, powerful question: what if we tried it this way? Our journey through levers, ramps, and rollers reveals a truth far more inspiring than any myth of lost technology. These ancient builders were the first practical physicists conducting colossal experiments in real time. They mastered force, friction, and mechanical advantage not with equations, but with intuition, perseverance, and an unwavering faith in collective effort. Their true legacy is not locked in the silent stones, but lives on in the very way we approach problems today. It is a legacy of observing a challenge, of iterating through failure, and of collaborating to channel simple principles into monumental results. Each monument they left is a frozen moment of human ingenuity, a conversation between a culture and the laws of nature. So the next time you see a modern crane against the sky or feel the smooth turn of a wheel, remember the long lineage of that idea, born when someone first placed a log beneath a heavy stone and discovered a better way. If this exploration of ancient problem-solving resonated with you, consider subscribing for more journeys into history's greatest puzzles. We would love to hear from you. Which of these ancient feats of engineering astounds you the most? Let us know your thoughts in the comments below.